As we dive into chapter 6 here, we'll see our second chapter on chemical bonding. A couple of new theories that we'll see in this chapter is valence bond theory. We'll discuss the pros and cons with Lewis structures and the pros and cons with Vesper theory. And then molecular orbital theory, which is our final theory on bonding. This is one that is the most difficult to grasp. We won't do too much in depth with molecular orbital theory. You'll do a lot more in later chemistry classes, such as organic chemistry. Our primary focus in this chapter will be looking at the pros and cons of all of these theories and how do they fit together to see a holistic view of chemical bonding. Now, where have we come from? Well, the first thing that we talked about in this class is quantum mechanics, and we've mapped out where the electrons are, specifically looking at the electron cloud and being able to say it's not just a swarming mess of electrons, there's a structure to it. There's orbitals. We had N, L, ML, and MS to be able to write out our electron configurations, fill up that orbital diagram, and we could see where the electrons were in the basic atom. Now, with bonding theory, we started to talk about the different types of electron behaviors, things like electron transfers to make ionic bonds, and electron sharing to make covalent bonds. What's great about this is it was very black and white. We said a metal and a nonmetal transfer electrons from the metal to the nonmetal, make ions, there's your electrostatic attraction. Covalent bonds we also talked about as being between two nonmetals, and they share electrons. All of those are driving to reach a noble gas electron configuration, which is stabilizing. With Lewis theory, when we talked about Lewis atoms and when we talked about Lewis structures, it's a very simplistic view of the connections for ionic and covalent bonds. It tells you who's connected to who and how are they basically connected, single bond, double bond, triple bond, things like that. Again, focusing on valence electrons as they are the electrons that go into reactivity, ignoring the core electrons. With Vesper theory, what we just talked about was how do molecules look in three-dimensional space? When we want to look at Vesper theory, what we're really trying to do is give the electrons the most amount of space that they can have in a three-dimensional model. We know that electrons repel each other, but they are attracted to nuclei. And so what we're really trying to focus on are those electron groups in Vesper theory. Now, with Vesper theory, there is a little bit of utilizing the chart. We can call it memorization if you want to be able to discern if I have 4 electron groups, oh, that must be a tetrahedral. But the real reason to why hasn't been understood until we get into valence bond theory. And that's where we're going to start. What happened to those atomic orbitals way up here in quantum mechanics? When we talk about these atomic orbitals, they don't just disappear when we make a molecule. And so that's where valence bond theory steps in. There are some issues with Vesper theory, and that's what we're going to talk about now. First, we'll talk about the problems with Lewis theory. Lewis theory generally predicts the trends and properties, but it does not give a good numerical prediction such as bond length and bond strength, right? It's a good idea to be able to approximate, but it doesn't always work. Lewis theory gives good first approximation of bond angles in molecules, but cannot be used for the actual angle. Now with Lewis theory, we cannot write just one correct structure for many molecules where resonance is important. And Lewis theory also doesn't predict the correct magnetic behavior for molecules. For example, in real life, oxygen is paramagnetic, even though when we look at a Lewis structure, it would predict it was diamagnetic. Everything is paired. Oxygen has its complete octet for both. And so what we really need, and in this Lewis theory, we are containing the idea of Vesper. What we really need is something to enhance. Specifically, what I want to be able to talk about is actual bond angles. There's been a disconnect between how did we get the bond angles in Vesper theory, and how do we even get those when we know bond angles or orbitals exist in the atomic realm as S's, P's, and D's, and F's. So here's a valence bond theory. It focuses its attention on what we call orbital overlap. I want us to think about a Venn diagram. If you've ever seen a Venn diagram, you know that it's two circles coming together and having an overlap. And there's the overlap, right? That is how valence bond theory describes a chemical bond, that we have these electrons in these these atomic orbitals, like S's, P's, and D's, and when they come together with another atomic orbital, they produce an overlap. I want us to think about this chart real quick. Energy on the y-axis increasing, and distance between two H atoms increasing on the X. So here we have an H atom and an H atom. And our job is to bring these two together in order to make a molecule, H2. Now, once they start getting closer, we start to see a little overlap. And here is where we see a great amount of overlap, right? Now notice that those nuclei aren't touching, the black dots are not touching, just the general s orbital that the two hydrogens would have contained. Get too close, and what happens to the energy? As we notice this energy path, as those two atoms are getting closer and closer, the energy is decreasing, and that's because of attractive forces. The electrons are attracted to the nuclei. Get too close, and what happens? Repulsion takes over. Electrons start to repel the other electrons. The two nuclei start to repel each other as well. There's what we call the perfect sweet spot right here, where this point, the point of lowest energy, where that point occurs corresponds to the actual bond energy and the bond length. This right here would be the internuclear distance between the two nuclei, or what we called the bond length. And up here is our energy released when the bond was formed, bond energy. It's also the amount of energy required to break the bond. So when we look at revisiting quantum mechanics, bonds between atoms should occur when the orbitals of those atoms interact. They need to overlap. They need to occupy the same exact space. And when they do that overlapping, we have to find the perfect amount of overlap. We can't get too close because then we start to repel. We can't be too far away because then we don't have enough attraction. And the kind of interaction depends whether the orbitals align along an axis or between the nuclei or outside the axis. So what we want to be able to talk about is there are going to be a couple of different types of overlap. This one that looks like a Venn diagram to me is our most straightforward type of overlap. When we want to discuss the different types of overlap, that'll be more geared towards when we're ready to start discussing molecular orbital theory. The first thing that we want to be able to look at is just this basic idea of, well, what type of overlap do I have? What atomic orbitals do my valence electrons reside in? So in valence bond theory, the valence electrons, right, create the bond. There's where we get the name. The valence electrons of the atoms in a molecule reside in a quantum mechanical atomic orbital. These are our s, p, d, and f orbitals. Now, what valence bond theory also brings about is the idea of a hybrid orbital. Some of the shapes that exist based off of our discoveries in Vesper theory don't make sense for S's, P's, D's, and F's. And so what valence bond theory does is it enhances what we know in the atomic realm and says that there could be a hybrid combination of these atomic orbitals. And a chemical bond results from the overlap of two half-filled orbitals. Again, one electron from each atom need to come together in this bond. So the geometry of the overlapping orbitals is what really determines the shape of the molecule. And this last one is where we really want to focus on. This valence bond theory is enhancing what we see in Vesper theory. So, basic idea here. Orbital diagram for the formation of H2S. Now this is a covalent molecule. S will be in the center because he makes the most number of bonds. We have H then on either side. If we wanted to count up our electrons, we're just doing the Lewis structure right now. Again, everything results from a Lewis structure home. If you're not comfortable with Lewis structures, you will not be comfortable with anything else in chapter 5 or 6. We have 8 electrons total. I'm going to put 2 electrons in the bonds between each hydrogen and sulfur. Then we complete the duets or octets of the outer atoms. Well, they're hydrogens, the duets are done. The other 4 electrons get placed on sulfur as lone pairs or non-bonding electrons. Now, what we can see here is that the 1 electron from hydrogen is going to be paired up with one of the unpaired valence electrons from sulfur. The same thing will go for the other hydrogen. Sulfur has 2 unpaired electrons in p orbitals. So what we can imagine with those p orbitals, there's the p orbital, it's got 1 electron in it. I'll just draw it on that top lobe. Hydrogen is going to come along with its 1s orbital and its 1 electron, and they're going to join together. If we want to imagine what that looks like in a Venn diagram, I'll keep the phases there. There you go. We could put the little electrons in there as well. I know it's a little squishy. Maybe I'll make it a little bit bigger for us. What we see there is the overlap between a hydrogen that was an s orbital and a sulfur in its p orbital. Same thing happens in this type of a diagram. We see that nice Venn diagram idea where each of the half-filled p orbitals starts to overlap with the half-filled s orbital. Now, what we would predict here with this valence bond theory is that the bonds formed are about 90 degrees in H2S. The reason for that is because when we look at the p orbitals, remember the px, the py, and the pz were on that 3D Cartesian plane, all 90 degrees from each other. And so that's where we can get that 90-degree outlook. And this is actually quite true. H2S has a bond angle of around 92 degrees. So it's very, very close. There might be a little bit of electron repulsion there from that last lone pair in the p orbital, but we see that there's a good organization about looking at valence bond theory, how the atomic orbitals overlap with each other. Now, if we were to use Vesper theory here, we might look at this Lewis structure and say that there were 4 electron groups, and that would be the tetrahedral, which would have a bond angle of about 109.5. A little bit less because of the lone pairs, but still around 109.5. Now, which one was better? Well, valence bond theory is actually a little bit better for us here. But what we want to be able to say is it's a marriage between the two that we want to be able to identify. Now, the main concepts with valence bond theory is that valence electrons of the atom in a molecule reside in quantum mechanical orbitals, S's, P's, D's, and F's, right? That's what we just showed. The or now, they may be in a hybrid combination of these. Why do we have Vesper theory where a majority of those 4 electron group models come in a tetrahedral with a 109.5? Where the heck did that 109.5 come from? It just didn't come out of thin air. Something must have constructed it when we see so many different 4 electron group molecules having the same random bond angle. So when we want to start thinking about the hybrid, we're going to have a couple of very important definitions for what a hybrid atomic orbital is defined as. Remember that an atomic orbital here, we might not have used that word for a while, but an atomic orbital is our S, P, D, or F orbital, where the valence electrons lie. So if we're talking about a hybrid atomic orbital, we are merging a couple of different types of plain old atomic orbitals. So I could take a combination of S's and P's and D's, mush them together, and we'll discuss what that means. Now, a chemical bond results when these orbitals interact, and there's a total of 2 electrons. And that becomes a new molecular orbital. This is where we start to see how molecular orbital theory will play a role in valence bond theory. Now, the shape of the molecule is determined by the geometry of those interacting orbitals. That's where Vesper theory, valence shell electron pair repulsion theory, is enhanced. All right. Now, according to valence bond theory, bonding takes place between atoms when there is an overlap. A couple of different overlaps I want to be able to talk about. It could be this direct overlap of atomic orbitals. So here's an s orbital and here's an s orbital. Let's bring them together. And they do a nice little Venn diagram right there. Now, another type of orbital overlap that we could see was with the p orbital and an s orbital. This is not hybrid yet. This is just overlapping of plain old atomic orbitals. We'll overlap that a little bit more. Being aligned along an axis. These would be aligned along an axis, this type of direct overlap. Now, what I like to relate this to is hand holding. The orbitals are literally holding hands. It's just like a relationship, right? Brand spanking new relationship, you want to hold hands. And the other type of overlap is not going to be this along an axis. Instead, what it's going to be is a parallel relationship. And the most typical parallel relationship we have is with our p orbitals, and it's here. This parallel relationship is going to be important for us. Now, when 2 p orbitals align like this, They should have one electron in each, and they should be attracted to each other. But notice how they're not technically touching. I call this a high school relationship. Not holding hands. I know I'm in a relationship with you, but I'm not going to touch you. I know, Lauren's insane. But the parallel relationship is weaker than the axis relationship. And so when we're looking at these two different types of relationship, we will see them come into play in valence bond theory as we start to describe Lewis theory, Vesper theory, and how the overlap occurs. So just note there are a couple of different ways that the orbitals can align. These are going to be our two main ways. We will call this that's aligned along an axis, we'll call that a sigma bond. A sigma bond is always going to be a very strong bond. It's that direct overlap. Here, I'll change the color so that it's back to the purple. It's that direct overlap of atomic orbitals, sigma. Also abbreviated with the Greek symbol sigma. The parallel relationship is going to be called a pi bond. It's abbreviated again, pi, just like the Greek symbol pi. We'll start to look at these orbitals and see how they come into play and when to be able to recognize them once we start drawing our 3D shapes again.